Hello, everyone. Welcome to this workshop on geochemical modeling for ore body knowledge and exploration targeting. My name is Juan Carlos Ordóñez Calderón, and today I'll be discussing a review of methodologies for geochemical data analysis. This is my bio for those of you who want to learn a little bit about myself, and my contact information if you have any questions following this presentation. My topic is going to be focused mostly on discussing methodologies for data analysis that include unsupervised and supervised machine learning. And the reason for that is that you can use these techniques to extract value of any kind of geochemical data, regardless of the digestion. You can use, for example, aqua-rigid digestion, 4 acids, portable, XRF, any kind of geochemical data, you can use these kind of techniques. But before I dive into this, I would like to introduce the concepts of compositional data in geosciences, in particular in geochemistry, and also discuss a little bit on the limitations of geochemical templates in the analysis and interpretation of geochemical data. So what is compositional data? Compositional data are vectors of positive component that sum to a constant. For instance, in geochemistry, which is a compositional data, you cannot have negative geochemistry. Also, if you were to analyze every possible element in a rock, you cannot have more than 100%. Even if you are using parts per million or parts per billion, if you analyze every element in a rock, you cannot have more than 1 billion parts per billion or 1 million parts per million. So that's two important characteristics: positive and constant sum. So this kind of data, also the most important information carried by this kind of data is relative. In other words, is the ratio between the parts that carry the most important information. It is also understood that the sample space for these compositional vectors or data is not the Euclidean space. It's different from the Euclidean space. And the sample space is the simplex. So let me break this a little bit for geologists. Sample space in statistics is basically the set of all possible outcomes of a variable. So in geochemistry, for instance, all possible outcomes of, for example, gold have to be positive. The outcomes cannot be negative. In contrast, for example, in the Euclidean space, the variables can be negative from minus infinite to plus infinite, 0. And that's not the case of the sample space for compositional data. So that means that a compositional data and geochemistry itself lie in a different mathematical space, which is called the simplex. So John Aitchison, in his monography, he developed this theory, and basically he has provided this sample space with what is known as the Aitchison geometry, or a set of mathematical formulations, also called simplicial geometry, so that we can measure things in the simplex as we measure in the Euclidean space. But in other words, in the simplex, you use a completely different set of mathematical operations. The simplex is equipped with its own algebraic geometry. For those reasons, we cannot just collect compositional data or geochemistry out of the lab and just throw that into multivariate statistical methods, because most of these methods are designed with the metrics that we use in the Euclidean space, but composition and geochemistry is not in the Euclidean space, it's in the simplex. So we need a different approach for multivariate statistical analysis. Other examples in geoscience of compositional data, in addition to geochemistry, is, for instance, mineralogy. Let me elaborate a little bit more about these concepts of the simplex. We, as geologists, are familiar with the ternary diagram. So imagine that the simplex is the generalization of the mathematical properties of these equilateral triangles or ternary diagrams into multidimensional space. So if you have 3 parts, you have a ternary diagram. If you have 4 parts, you have a tetrahedron. If you have multiple parts, D parts, then you have a hyper tetrahedron lying in a bigger dimensional space. But you can also have a small, 2-part composition or a 2-part simplex, which will be a line segment. And as I explained before, this simplex is equipped with an alternative geometry, which is called the Aitchison geometry or simplicial geometry. In other words, there are a series of mathematical operations that are unique to this kind of sample space. Here is just a more formal definition, a set builder definition of the simplex, and basically what this reads is the simplex in D dimension is the set of vectors D with D components. All these components are positive and sum to a constant K. So if you have, for example, your data coming from the lab and you want to analyze just a subset of those elements coming from the lab, you can use what is called the closure operation, which is basically close that subset to sum to a constant, and that closure is basically reprojecting. If you have, for example, 40 elements, is reprojecting that 40-part simplex into a smaller simplex, for instance, a ternary diagram 3-part simplex. So the closure operation is just reprojecting. So the point here is that as you move from, for example, 40 parts, 10 parts, 3 parts, this kind of subcomposition should behave like orthogonal projections. In simple words, is like if you have 2 points in a space, let's say in 3-dimensional space, the distance between these 2 points, as you project them to a 2-dimensional space, should be the same if you are projecting these 2 points parallel to the plane where you're projecting, or it should be smaller if the projection is oblique, but the distance shouldn't be, as you project these spaces to smaller spaces, the distance shouldn't be larger. So this is basically what it means, and it has to do with being able to measure objects coherently. I think a graphical presentation of this is much more intuitive. So let's say you get these 2 elements from the lab, sodium and calcium, and you decide that you are going to be working in that space. You do the closure operation and close to a constant 100%. So now all these data points are going to look like a line segment, 100% calcium, 0 sodium, 100% sodium, 0 calcium. Just to understand what the closure operation does, here I put in red the actual data cloud, and in black the closed data, which is the line segment or 2-part simplex. Basically, each of these data points in the simplex represent a family of points. For instance, if you take the point here in this line segment that is intersected by this line coming through the origin, but you see that there are many points along this line that would project in the same point in the simplex. So any point in the simplex is a family of points, and all these points along this line that project in the same place in the simplex, all these points have one characteristic, and is that they have the same ratio of the 2 parts. So when we are looking ternary diagram, line segment, when we are looking in the simplex, these data points really represent family of points, and the information that they carry is relative, which is the ratio between the parts. The constant that you choose to close the composition doesn't matter. For example, here I close to 1,000, here I close to 3,000. The relative information is not going to change. In other words, you can decide to work in percentages, you can decide to work in parts per million, part per billion. As long as all the elements are in the same units, it doesn't matter the closure constant when you are doing your work. You should get the same results. This is just to gain that intuition of a 3-part simplex. You have here 3 elements, and they look like they occupy this volume freely, but not really, because these elements are coming from a larger compositional space. But when you reclose these 3 elements, you see that they define a plane, and this plane is basically a ternary diagram. You can see the shape of a ternary diagram here. So this is basically what the closure operation does. As you close your composition to smaller or larger dimensions, you are basically reprojecting your composition to a different simplex. So I mentioned earlier that the simplex has its own algebraic geometry, its own vector space structure. What this really means is that if we remember when we were taking school, regular mathematics, we learn that about summation of vectors, we learn about multiplication, we learn operations to measure distances between the points, etc. Well, all those operations is what define basically a kind of a Euclidean space. And those operations also exist in their own mathematical formulation for the simplex. For instance, summations between vectors in the simplex takes the form of a perturbation, where you are basically multiplying each component of each vector. If you're multiplying a vector by a constant in the simplex, that becomes taking each component and powering that component to that constant. And so all these other operations that we are familiar in Euclidean space, they also have their equivalent, their representation, their mathematical formulation, special for the simplex. All these mathematical operations is what define basically a kind of an Euclidean type vector space structure for the simplex. And this kind of was realized in the late 90s, early 2000s, that really what John Aitchison has done was providing this kind of mathematical space with a vector space structure, again called Aitchison geometry or simplicial geometry. Just to kind of emphasize, if you were to, in this ternary diagram, if you were to plot these lines that represent alteration trends towards potassic alteration, for example, sorry, about enrichment in potassium, if you want to plot these lines, you wouldn't be using the traditional equation of a line in Euclidean space. You will be using an equation that honors all these mathematical operations in the simplex, where multiplication by a constant is powering and summation becomes a perturbation. So that's more or less the inclusion here. But it can be overwhelming because then you have to, if you're working in simplex, you will have to learn, new mathematical formulations for all the mathematics that we have learned in Euclidean space. Now we have to learn different mathematical formulations when we are working in the simplex. So researchers have basically developed a series of mathematical representations called based on log ratios, and the objective of these mathematical representations is to kind of open the compositional data to the real space so that we can use traditional Euclidean geometry to analyze our data. So a series of representations have been proposed. This is the additive log ratio, where, for example, you take your geochemistry and divide every element by a chosen element. In geochemistry, we normally choose, for example, an immobile element depending on the analysis, and then we take the natural logarithm. It's very simple representation. The problem with this representation is does not preserve distance because it's not an orthogonal projection. So if you were doing cluster analysis, you don't want to use the additive log ratio, for example. The central log ratio, which is basically taking each component, or in this case, each chemical element, and dividing by the geometric mean of all the elements on that sample, and taking the natural logarithm. And this representation is very interesting because it does preserve distance, so it's amenable to do, for example, cluster analysis. One of the problems is that it has a singular covariance matrix, which in other words means that you cannot invert this matrix, and many statistical methods for multivariate analysis require inversion of the covariance matrix, so that generates problems. And then this isometric log ratio representation, which has very important properties because it's indeed an orthonormal coordinate system. In other words, if you do this isometric log ratio representation to your data, now you can use all the mathematics that you have known without any worries, because this being an orthonormal representation, if basically the Euclidean geometry is appropriate once you have this transformation. It has been criticized because depending on the basis that you choose to reproject your geochemistry or your data, it might be difficult to interpret. So the proposal has been that these isometric log ratio representations can be plot as planned balances, where if you find a meaningful combination of log ratios, then you can use this equation to create your plant balances, where R and S represents the number of elements in the numerator and denominator, respectively. And this is the geometric mean of the elements in the numerator and the geometric means of the elements in the denominator, and of course, taking the natural logarithm. So if you find a good projection, a good plant balances, then you can use this isometric log ratio coordinates and use your analysis. So the proposal is basically these ILR coordinates, also called coordinates because they are orthonormal coordinates. So basically you can imagine that if this is your geochemical data set, when you reproject this in coordinates, then you have, this is in the Euclidean space or ILR coordinates. So the proposal is that you work in coordinates. You do all your statistical multivariate analysis in coordinates. In this case, all these colors represent clusters, and these clusters were done in isometric log ratio coordinates. But you do your interpretations back transforming this into the simplex. So in other words, it's the principle that you work all these mathematical operations in coordinates, but you interpret in the simplex. I personally also recommend that approach. So a series of other important motivations to really honor the compositional data of your, the compositional characteristics of your geochemical data is the problem with the spurious correlations. This is, I think, one very important motivation to use compositional data analysis. This was first discovered by Carl Pearson in 1897 and then rediscovered by Felix Chase in the 60s and basically addressed thoroughly by John Aitchison in the 80s. So if you get your geochemical data analysis from the lab and then you are confident that these three elements are going to give you the results you want in your analysis, and then you see that out of the, of the 45 elements that you get from the lab, all these three elements have positive correlations. But let's say you decide to close it because you are plotting this in a ternary diagram, doing analysis, etc. Just the closure operation on these elements to project it into a three-part simplex, then you see that you induce negative correlations. So now some elements like aluminum and iron, aluminum and titanium, aluminum and iron and titanium and iron are negatively correlated. So that wasn't present before. And you don't know how this is going to change. As you change your composition, all these correlations are going to change. So correlation analysis is not really appropriate for compositional data. The other important motivation is a problem that has to do with distances. In geoscience, we use distances a lot for different purposes, including cluster analysis. So I simulated this data set here to show, starting from protolith 1, I added the same mass of silica and extracted the same mass of silica to create a series of alteration steps where silica is added to a rock that is composed hypothetically only of silica and aluminum. The whole idea is that each next rock has the same proportionality of alteration. But as you can see in this diagram, it seems that there is more alteration from 1 to 2 than from 2 to 3. And we know that this is not true because we created this data set and that's not how we did it. But when you represent this in a central log ratio representation, for instance, you see that all the points are equidistant. And that means that each and every rock was formed by the same kind of intensity of alteration. And that's exactly how we created the data set. So if you were using raw geochemical data here, in a cluster analysis, you will not be getting the actual geological process that form this data set. So that's another motivation to use compositional data analysis, in particular, because distances are deformed in the simplex. This is a line segment, so this is a simplex, and this is in CLR coefficient. So you see the difference. You can see better the geological process in the log ratio representation. So finally, to kind of wrap up with the compositional data part of this talk, it's very important to understand that when we are analyzing a data set, in this case, geochemistry, these data sets belong to a sample space. and that any metric we use to measure, any property or differences between objects in this sample space needs to be appropriate for this sample space. In this case, this is how these data points are visualized in the simplex, and this is how they visualize in isometric log ratio coordinates. So if you don't use the appropriate metrics for the sample space that you are working, you're possibly going to miss some gemstones hidden in your data set. I added here some references on the fundamental development of the theory and some other applications in geochemistry for those interested in doing compositional data analysis. So the other topic that I would like to address is template-based geochemical analysis. So what is really template-based? Throughout many years, geoscientists, geochemists have developed numerous templates to interpret geological attributes. And in today's world, open source software and commercial software has kind of virtually automated almost all of those templates. So you are basically a click away from plotting your data into these templates, and you're basically ready to start doing interpretations and understand what your geochemical data is telling you. For instance, these two diagrams are proposed for mapping alteration in porphyry and VMS systems. And these two diagrams are more geared towards identifying lithologies. This was in volcanic rocks, and this one in skarn systems where you have siliciclastic rocks, limestone, dolostones, and a series of a combination of these chemical and siliciclastic sediments, like different type of marlstones. So there has been a lot of effort to provide templates, and you can easily plot this just with a click of the mouse, your data set into these templates. However, this kind of analysis is limiting for several reasons, and is that most of these templates have been designed for a near total or total digestion. So in our line of work, sometimes we work in a mine or in an exploration project where we actually didn't collect the data. It's legacy data, and maybe all what you have is aqua-rich digestion. Maybe all what you have is PXRF, and some of these diagrams won't, and most of these diagrams won't work because they were designed for a total or near total digestion. So that's one of the limitations. And also there are a lot of assumptions encrypted in these diagrams that sometimes are not really well understood, and however the data gets interpreted. Let me just put some of the assumptions. In addition to the digestion assumptions that I mentioned, element mobility assumptions, weathering, etc. So let me just show you a few of the assumptions from my point of view, some that is very simple to some a little bit more complex. So the digestion assumption, for instance, these two are the same rock types. This one's analyzed by 4 acids, this one by aqua-rich digestion. So in the 4 acid, which is the actual, the digestion that should be used in this template, you see this is a porphyry exploration project. You see mild sericitic alteration, mild argillic alteration, but this totally changes in aqua-rich digestion, very strong argillic, very strong sericitic. And this is just because this template is not appropriate for aqua-rich. So this interpretation would be completely wrong. It seems simple, but I still have in my experience working in projects where there is no metadata of the geochemistry. So you don't really know how it was analyzed. And that's very important. So this kind of problems still happen, even they seem very simple. A little bit more complex is when you look at this diagram, this is a gold exploration project in a very weathered terrain. You see kind of two groups of rocks, one on the kind of felsic intermediate and the other one in the kind of more alkali intermediate as well. So if you uncritically plot and use this diagram, then you will be interpreting two different lithologies. But in reality, when you kind of do a deep dive into this data set and you look, for example, at the more weathered rocks, which are more than 50% of the samples in this project, you see that out of these 4 elements used to build this diagram, niobium, zirconium, and titanium were immobile, but yttrium was significantly lost and remobilized during weathering. So what that does is basically you are changing the niobium-yttrium ratio, and you're moving your composition towards a tracheandesite composition. But this is just weathering. This is not a magmatic process. This is, in other words, what the interpretation you're getting from this diagram is wrong, because one important assumption in this diagram is that all these elements were immobile, and this has been violated due to extreme weathering. So you will be doing an incorrect interpretation if you don't do, for example, a very careful trace element mobility analysis in your project. Another limitation that is less evident is this is another gold exploration project in a kind of a intrusion related project. If you plot the data, you see that it forms a really nice cluster around a single lithological component, kind of a alkaline mafic rock, very homogeneous cluster. But when you use compositional representations, basically what you see that really in this kind of seemingly homogeneous cluster, you have at least two or even more different clusters. So there is at least two lithologies here, and possibly more in this particular area. So if you just kind of base your study on available templates, then you will be missing really some of the data structure that is telling you that there is more lithological types in this area than just a single lithology. In general, I think the message that I'm trying to leave here is that geochemical templates are good for initial data exploration. Sometimes they really solve problems, and that's good. But the point is that they are generalizations, and every mineral deposit is unique. Every ore body is unique. So really, you capture this uniqueness when you set your analysis using more, a multivariate statistical analysis, or a statistical learning, machine learning methodologies. When you take an approach like multivariate approach, you can really start breaking these data patterns in your data set. And by the own nature of this kind of analysis, you are actually tailoring the analysis to exploit the particularities of your data sets. You are not just using generalizations. So my analogy is like buying a suit, basically buying a unique size fit all and pretending to be or expecting to be well dressed. So the whole point here of this kind of a statistical learning methodology is that you will be fitting your analysis for tailoring your analysis for purpose, instead of using just generalizations. So I'm not against using the templates, but they are generalizations, and possibly you will meet some important information in the data that is only amenable when you really take a multivariate statistical approach. Some reference here on some useful templates for characterization of alteration and lithologies, if you want to follow up with that. So the other part of this presentation deals with now the actual machine learning or statistical learning methodologies, and there are basically two paradigms. We have the unsupervised learning and the supervised learning, and I'll explain kind of briefly some case studies using the two paradigms of machine learning. So, but let's define what machine learning is. I'd say that there's not really consensus, but in my view, this definition kind of, if not the best, it really highlights some key points, and is basically an algorithmic modeling approach in which we learn an output from our data sets. So this learning and output is, for example, you may want to learn to identify alteration in your data, or a lithology, or an gold pathfinder anomaly, etc. We use this to evaluate learning tasks using metrics of model performance. So we we can evaluate if we are identifying correctly. We can measure. You can assess the quality of these models. More importantly is that you can automate this learning model. So once you develop a model, you can reuse it. And ultimately, we do this because either we want to approach human learning or exceed it. So we want to be able to increase our productivity by approaching, what a human can do, for example, identifying an alteration, or we want to exceed that, that ability using this kind of algorithmic model. So let's get started with some examples of unsupervised learning in geochemistry. So what is the goal of unsupervised learning? It's really, in a nutshell, is pattern recognition is one of the main goals. And the idea of pattern recognition is because if you think of your geochemical data set and all these multivariate structure, the patterns hidden in your data set really reveal geological processes. So if you are able to map patterns in your data sets, most certainly you will be identifying geological processes, whether it's alteration, mineralization, lithological units, stratigraphy, etc. And to be able to delineate those patterns, there are techniques that we use that are called cluster analysis. So we have k-means, k-medo, fuzzy clustering, hierarchical clustering. There are different techniques to partition this geochemical space into patterns that reflect these geological attributes. This workflow is the workflow I use. It's not necessarily the only workflow that exists out there. I personally recommend it. I use it. I have used it a lot with good success, but it's not unique. You can develop your own workflows. And the way I start the analysis is basically starting with a fundamental question on what is really the learning task. So, for example, if I get this geochemical data set, I want to say, okay, I want to map alteration. Is that my learning task? Or I want to map the stratigraphy, being able to identify rock units, for example. With that in mind, then you have to obviously do all that data cleaning, data imputation, missing values, etc., and define a geochemical space. This is very important because this depends on your learning task. If your learning task is an alteration, the geochemical space is completely different from identifying stratigraphy, for instance. So in order to define these geochemical spaces where you are going to solve these problems through unsupervised learning, you do kind of some people do principal components. You can also do Q-mode clustering, which is basically clustering all the variables, all the elements, and finding these associations in the elements using your geochemical knowledge to understand what associations may represent these geological processes that I want to map. And obviously, the ultimate goal is mapping them in 3D or in 2D. Once you have decided your geochemical space, you do what is called feature engineering. In other words, you create variables, either compositional representations like isometric log ratio coordinates, or maybe you want to use principal component analysis. Principal components are also isometric log ratio coordinates if you do that compositionally. Or maybe you want to reduce the number of components to do your clustering, etc. And then finally, the cluster analysis. The point here is that there are numerous ways that you can use to evaluate the quality of your clusters, but the most important as our scientists is validating these clusters in geological space. Even if the clusters are mathematically correct, and I'll show some examples, some clusters might not be geologically sensible, so you have to, if they don't speak the geology, they are not, you have to go back and define your geochemical space and see why is that. It's more important, in my opinion, the cluster validation in geological space than just the mathematical validity of your clusters. So here's some of the workflow. So this is an example already published of the Rosemont deposit. This is the variation matrix of the Rosemont deposit. The variation matrix is part of the mathematical tools to work in the simplex, and it was proposed by John Aitchison in 1986. And basically, it is the regular variance of all possible log ratios. So a very small value in the variation matrix or tau value, it represents a strong association. So obviously an element against itself is very strong association, so it's 0. So a small value means very strong association, and a larger value means almost no association or less association. So I color coded here by columns, the lowest value meaning the strongest association. So as an example, this is a skarn deposit. So calcium has the strongest association with magnesium, which is kind of expected because there are dolomites and limestones. And then lanthanum has the strongest association with cerium, which is also expected because there are sediments and volcanoclastic rocks intercalated where we have the two light rare earth elements are obviously associated. So you see that this really showing you how these different elements relate each other. So we use that for, we can plug this variation matrix for Q-mode clustering, where we are really clustering variables and see what's the interrelationship of these variables. So this is obtained through Q-mode clustering of the variation matrix. This is not the Rosman deposit. This is another deposit, an epithermal deposit in Chile. This is a for acid digestion. So we did the same methodology, did the Q-mode clustering, and we created this geochemical space. And the fundamental question here is mapping lithology. So we created this geochemical space, and this is the projection of a 3-part simplex into isometric log ratio coordinates. And you see basically 5 clusters. And the clusters were done in ILR coordinates or balances. So you can see, for example, that some clusters that are single clusters in geochemical space, they break into 2 clusters in geological space. This is not a cartoon. This is actually a leapfrog model built in 3D. And this is approximately 1.5 kilometers long. And these blocks represents gold blocks at 0.7 ppm. So you see that some clusters in geochemical space are single, but in geological space, they split into 2. Some other clusters like 3 and 5 are distinctive in geochemical space, 2 different clusters, but they are intercalations in geological space, so basically form a single unit. So yeah, you can have these clusters in geological space may coalesce these clusters in geochemical space may coalesce in geological space or may split in geological space. So that's the point about this. So, but how we interpret this? Well, definitely this is a volcanoclastic sequence, and we have it very slightly deep into the south. Have an unconformity here, but interpreting these ILR coordinates is relatively difficult. So, as I mentioned earlier, you do all your analysis here and then interpretations in the simplex. So this is back transformation of that coordinate space to a simplex. And here is much easier to interpret. We can argue that we have 2 lines. We have a compositional lines from 4, 3, 1, and 5 to this end. Then we have another compositional line which only fits cluster 2. 2 points about this is that more mafic rocks are here, more felsic rocks are here. So all these rocks, 4, 3, 1, 5, they kind of represent some sort of a fractionation of these rocks have been derived through, kind of a similar magma series that has been fractionated. They're not necessarily a liquid line of descent, but they are related somehow by the same kind of fractionation of similar magmas, where this one is completely different. The cluster 2 is different magma. And this kind of volcanic breaks normally result in this kind of unconformity. So you see that cluster 2 actually form a distinctive also geological process. So these are the kind of information you get. It's much easier to interpret in the simplex than in isometric log ratio coordinates. But if you do a clustering in coordinates, then you know that you are working in Euclidean space mathematics, which is not gonna be a problem with your interpretations. This is an aqua regia digestion following the same methodology, creating, I always insist in this, which is engineering geochemical spaces. The reason for that is when you look at in the literature, there is a lot of journal articles where people plot, use all the geochemistry, like 45 elements into a principal component analysis, and people start doing clusters and start finding meaning. I think the proposal here is the opposite. Is you do your geochemical analysis, you create and engineer a geochemical space where you can actually answer a question easily and not trying to find meaning in a series of principal components. So here, for instance, we decide a geochemical template for alteration using isometric log ratio coordinates. And here we decide a geochemical template for metal zoning using also isometric log ratio coordinates, but all the target and pathfinder metals, where here we are using major elements, including aluminum, that kind of reflect that chemical change during alteration. More importantly, what you see is that same geochemical data set, different geochemical spaces, you get different geometries in geological space. The length of this block is around 1.2 kilometers. So you see the alteration. This is also an epithermal deposit. Remember, this is aqua region. And you see this kind of vertical temperature gradient where you have the chloritic zones, phyllic zones, argillic, and calcic alteration zones. This calcic alteration zone is actually a late remobilization process where sulfur was remobilized and deposited as gypsum. So if you were to try to solve this kind of alteration system using an available template, you cannot do it because first, this is an aqua-rigid digestion, and second, normally a lot of these templates are oriented genetically. So kind of a gypsum alteration zone called here calcium is not going to be located because this is not what is understood in the genesis of an epithermal deposit. These are processes that later impact your mineral deposit. The point is that these units are very important. This was done for metallurgy because when you have this calcic, this gypsum, if you grind too much gypsum in your leach pad, it can cement your leach pad. And also some of the strong argillic alteration may reduce the hydraulic conductivity of your leach pad. So we are interested in actually modeling alteration that is part of the evaluation of the value drivers of your deposit, not just understanding how it forms. It helps understand how the deposit forms, but also providing an economic connotation. And here we have this completely different geometry where we have here flat line geometries. We have this kind of ring fold geometries where, you know, the ore body, the actual grades are kind of lined into a ring fold structure, kind of subvertical ring fold structures. And this is very typical in volcanic terrains. So a model like this will be supporting, for example, resource geologists for estimation. A model like this will help also metallurgists, for instance. So can we confidently model geological attributes using aqua regia? I think the answer to this is yes. However, when we are using an aqua regia digestion, as I showed before, you have to do a very strong due diligence to understand what the digestion is doing. You just cannot plug elements into an analysis. And so I'm going to share some experiences here on this project. It's a gold mine in a very weather environment, basically lateritic environment. So we developed this geochemical diagram using the methodology I just explained to map, for example, footwall. This is cluster 5. Cluster 3 and 4 are basically the main sulfide ore, and then these two clusters 1 and 2 are the oxidized ore, or the extremely weathered rocks are cluster 1 or 2 benches, just this top part of the regolith. This is approximately 150 meters. So the very top layer is the most weathered, but there is approximately, you know, 70 meters of weathering. So the importance here is that weathering really impacts recovery. If you see here, you see how the extremely weathered rocks in these two clusters, they exhibit the lowest recovery, especially the rocks at the top of the regolith, which are the most weathered rocks. So we use this classification to help metallurgy, also geology, resource estimation, but the whole idea was to use this in additional sampling, pair this knowledge with new metallurgical tests for further flotation tests, for example. But then when we got the results from the new samples, this is what we got, which kind of nonsensical, because why would we want to sample the footwall, which is low grade or barren? Indeed, what we took, the samples we took should plot in the cluster 3 and 4, and mostly cluster 2, some cluster 1. But why that happened? So sometimes when that happened, people immediately blame the aqua regia digestion. So doing the due diligence, what we realized is that we have these samples were analyzed, crushed by the lab, pulverized by the lab, 35 microns, passing 90%. But regular geochemical data analysis is done at a particle size of 75 micron, 85% passing. So when you crush a lot, then aqua regia digestion will digest more of these refractory elements, and you will be switching the composition towards this end member. So when we ask the lab to match the baseline geochemistry in terms, not just the analysis, but also the particle size, then we got the samples classified in the right spots. So you have to be really mindful when you use aqua regia. It's not just, you have to be more careful on the quality control, including pulverization, to be able to obtain meaningful results. What I recommend sometimes if you get data that is not total digestion, then you can get into problems interpreting that data. What I recommend is to do a due diligence. This due diligence comes from an exploration project where we wanted to know if we could use aqua regia, to save money, because there are some aqua regia packages where you can use 30 to 50 gram pulp, and then you get gold plus all the elements by aqua regia. And that's possibly going to cost you half of the price or 1/3 of the price as using, for instance, a fire assay plus 4 acids. So we wanted to explore that possibility. If budget is not an issue, you wouldn't be doing that. But maybe you have this kind of data sets that are legacy data, so this due diligence is important. So if you have patterns like this, like yttrium, where in this particular project, this is not generalization, this project by project, where you have the total digestion, either 4 acids or fusion, matches very well the aqua regia, or where there is this relative association where high values in aqua regia are high values in fusion, low values correspond to low values, then you can feel free to use these elements in any geochemical analysis. For instance, you see here especially how scandium is mapped in aqua regia and fusion. So you would be able to definitely develop good interpretations out of elements that behave like this. Elements like pattern 3, where there is, like here, zirconium, where you have no association, a lot of scattering. There is a lot of matrix effects. So the information carried in aqua regia is not just geology, it's also digestion and a lot of processes that you cannot control. So I don't recommend using this in your analysis because it's going to produce noise. Sometimes patterns like this, where you invert the pattern, you see, for example, titanium, high titanium in aqua regia corresponds to low titanium in the total digestion, and vice versa. So why is that? In this particular project, what happened is that extreme weathering, it really changed this composition. How? Well, if you think the fresh rocks in here in black and blue, the fresh rocks still contain pyroxene, amphibole, biotite, and these elements have trace titanium. And these minerals are amenable to be digested by aqua regia. So some of that titanium is going to end up in the aqua regia digestion. But if you take the same rock and extremely weather that rock, then titanium is immobile. It remains in the soil. Actually, it will increase residually in concentration, but it's now present in minerals that are anatase, for example, titanium oxides. And these titanium oxides that form after the extraction of amphiboles, biotite, etc., these titanium oxides cannot be digested in titanium. So evidently, the rocks that have less titanium are going to have higher aqua regia titanium because that titanium can be dissolved. But the rocks that have even more titanium, they will report less titanium in aqua regia because that titanium cannot be digested in aqua regia. So if you understand that, you still can use these kind of patterns. Let me just show you how it looks in space. In space here, this is the fusion or for total digestion. You see it's mapping very well the intrusion that scandium is mapping. But you see how titanium is switched to these areas in the aqua regia space. Well, because these areas where the intrusion is the most elevated areas where you have the most weathering. So here, there's a lot of titanium oxides, and therefore aqua regia will not be able to digest that and will show like a titanium low. So these are the kind of things that need to be understood when using aqua regia packages. You need to do your due diligence, because I think at the end of the day, you still can use titanium here, but normally when we think as geochemists, titanium is, I can use it for lithological mapping. But here, aqua regia completely changed the meaning of titanium. Here means that you can only use titanium if you're going to map weathering, not necessarily lithology. So so if you use it in a conventional way, you're going to be, your analysis are going to be wrong and will be blaming the digestion. Just for those interested, this is what we got for gold, aqua regia, and fire assay. So in this particular project, we were confident that we can use aqua regia, a 30-gram or 50-gram package, to map lithology, mineralization, etc. In general. Obviously, if the goal of the analysis, geochemical analysis, is all these stoichiometric relationships between minerals, then we shouldn't be using aqua regia, because these stoichiometric relationships are not preserved in an aqua regia digestion, because the digestion is partial. I would like to emphasize the role of geochemical literacy in all these kind of supervised and unsupervised analysis. I already explained this example where we did, all the geochemical analysis, all the compositional analysis to define this kind of shallow line stratigraphy. This is the same example, but instead of working on the trace element mobility, for instance, in these particular projects, argillic alteration really remobilize yttrium. If you keep those elements in your clustering, this is the kind of shapes that you get. So instead of getting this cluster one really nice shallow line stratigraphy, you will get kind of an amoeboid shape stratigraphy, which is totally, actually the cluster is mathematically correct, but it's geologically nonsensical. Now, if you get into, the 45 elements coming out of the lab, do cluster analysis of the principal components, you get a flat line stratigraphy. Because you are not really, by doing this, you are not really thinking on a geochemical space for a question. You're just trying to fish for meaning and get all these nonsensical results. So indeed, I think we need to let geochemical analysis guide algorithmic modeling. We cannot allow algorithmic modeling guide geochemical analysis. So the last part of the topic will be on a summary of supervised learning. So we already kind of have a broad view of what unsupervised learning is, finding patterns. So what really is a supervised learning? In supervised learning, we care about predictions, and then we have response variable and predictor variable. For instance, a response variable is what we want to predict. See, if you want to predict alteration, or maybe you want to develop a model to predict the percent of clay minerals to support metallurgy. So that's the response variable. And the predictor are the variables that you are using to predict. In our case, it's geochemistry, but there can be many predictor variables. For instance, your predictors can be numerical, can be like geochemistry, mineralogy. Categorical, you can inform also your predictive models with, if you have information about the stratigraphy or alteration. And the same goes for the response variable. Maybe you want to predict stratigraphy or oxidation, but you can also predict a numerical variable like metal recovery, mineralogy, bond-wear index. The difference of this analysis is that here we have the response and predictor variable, but in unsupervised learning, we are just learning patterns in the data set. Here we have a specific task, is we want to predict this, for instance. There are numerous algorithms that you can use for supervised learning, including all the ones that I have listed here. These last three, k-nearest neighbors, classification and regression trees, and random forest, are also amenable to be used either for predicting categorical or numerical variables. And in recent years, there's been a lot of tests in geosciences, and random forest has become one of the top performing algorithms. So you can almost you almost are not wrong when you're using random forest for a predictive task. It's a very powerful algorithm. I'll show an example of that. And I think part of another important thing to emphasize here is that it's about prediction, not explanation. So, but when I mean no explanation, I don't mean we are not aiming to explain geology. We do want to explain geology, but we don't want to explain the mathematical model. If you're familiar with regression analysis, we can explain a regression saying the intercept is X and variable X multiplied by, you know, by a coefficient X, and then you know how much each variable is contributing to a model. That's not often possible in machine learning. It kind of takes the form of almost a black box, because you are so interested in the prediction that sometimes some of these models are ensembles of models, many models. So you are not explaining the model, but you are more interested in evaluating if your model can predict. Here is a kind of a methodology that I also follow. Is something that I would recommend, but everyone has their own way to do things. I always, as I explained, start with a fundamental question, like what I want to predict. In this case, I want to predict mineralogy, for instance. Then it's very important in this kind of supervised learning, understanding if we have a good baseline geological sampling. And by this geological sampling, taking the actual sampling of geological materials in the field. I think I sometimes sense a lot of false expectations, and is that these models can actually save you money on sampling. No, these models help you use better your data sets, but you still have to do your sampling and make sure that under the variability of the property that you want to predict is quantified, because otherwise you cannot predict that unsampled variability. So once you are confident that your baseline sampling, if you want to predict an alteration, you make sure that every areas in your ore body have been characterized, have been sampled, so that you can predict confidently alteration. Then you can do all this kind of data wrangling, as I explained before. Feature engineering, it bears similarities with the unsupervised learning. You can create features, either principal components, isometric log ratio coordinates, Q-mode clustering. And obviously you have to decide whether it's a categorical or a numerical variable that you're predicting. When predicting categorical variables, it's very important to have data sets that are balanced. For instance, if you're predicting oxidation and fresh rock, and you have 1,000 data points in oxidation and 20 data points in fresh rock, then your data set is in balance. And there are statistical tools to balance data sets, but I think I want to emphasize that these statistical tools are not a solution to poor sampling. So in the example I gave, 1,000 versus 20 samples, you need to sample. These statistical tools for balancing a data set are good when the imbalance is because maybe some areas have been oversampled. For instance, in the same example, maybe you have 10,000 data points in oxide and maybe 3,000 data points in sulfide. Then maybe you oversample oxide. So you can use statistical techniques to rebalance, to make sure that the two data sets have more or less equal samples. But these statistical tools are not meant to get around poor sampling practices. The next stage, obviously, is doing a statistical resampling, basically splitting your data set into training data set, test data set, validation data set, and basically what you aim is that you train your model with a set of samples, you set another set of samples apart so that you can evaluate the performance of your models in a set of samples that was not used in the training data set. And that's called cross-validation. And finally, again, once you have evaluated mathematically the performance of your model, you have to evaluate that in geological space. And in many cases, in these kind of predictions, if the model do not perform well, is because the baseline geological sampling is poor. You need more samples, basically. There's no way around to that. So yeah, and poor sampling practices can cause these kind of imbalances that is going to affect your model, the development of your supervised learning models. I want to emphasize this because we cannot predict and sample geological variability. And that's an issue because sometimes I have projects where people want, for example, to predict geological property in an open pit, but they have a lot of samples in the northern wall of the pit, but not many anywhere else. So you cannot do that. You need to have what is called an appropriate characterization of the geological variability through your sampling in order to build good and robust predictive models. So this is a kind of a workflow on combining supervised and unsupervised learning methodologies for prediction of skarn alteration, and also an example of the Rosman deposit. So the very first stage, basically, we have 1,000 samples with mineralogy and geochemistry, XRD mineralogy. So we wanted to develop a skarn alteration model out of the mineralogy, so it's quantitative. And then we want to use this collocated, variable with mineralogy and geochemistry to train that model so that we can predict this alteration system in the rest of the deposit, which has approximately 35,000 samples with geochemistry, but not mineralogy. So we're using these 1,000 data points with mineralogy and geochemistry to build a predictive model and then export that model to the rest of the deposit. Again, we use the same. Is mineralogy, is also compositional. So we use the simplex isometric log ratio coordinates like here, cluster analysis, and we develop these kind of 4 clusters, which is the garnet pyroxene skarn, the serpentine amphibole skarn, the epidote skarn, and any sample with less than 10% alteration minerals, then we call it least altered because everything is altered basically. And basically that variable that we created is what we are going to use. We created this through unsupervised analysis, and then we're going to feed that variable in a supervised analysis for prediction. And as I explained, we split the data into training and test sets. We created 10 test sets, different chunks, so that we are fitting the model 10 times in 90% of the data, and evaluating the performance of the model also 10 times in 10% of the data that was left out of the fitting process. And this is done to evaluate, the bias and variance of the model, just to understand what is the model variance and bias. This is a synthetic data set. This is not the project, the Rosman project. It's just synthetic to explain the intuition. So basically, there is 100 points that I created here, and I extracted 12 data points, and I fit 2 models. So you see that the model in red has lower bias, has lower error than the model in blue, and the model in red almost follow every point. Actually, the model in blue has 73% more error than the model in red. So this is in the training, but when new data comes, test data comes, then it happens that the test data has 200% more error than anticipated in the red model, and the blue model has 20%, only 20% more error. So in other words, even the model in red has lower bias. It has huge variance because in order to get a good result, you will have to retrain the model, whereas the model in blue is very stable. So there is always a trade-off between if you make your model to fit too closely every data point, you are going to overfit, and the model is going to have very low bias but extreme variance. So you cannot predict. You want something that makes some mistakes, but it's more stable. So a trade-off between bias and the model variance. That's basically what it means. So this is going back to that example of the skarn deposit, and we use all these algorithms, support vector machines with linear and radial kernels, quadratic discriminant analysis, linear discriminant analysis, classification and regression trees, random forests. We fit the model. Each model was fitted 10 times, and there are 14 models. Fitted 10 times in the training set in blue here, and fitting 10 times in the test set to calculate the accuracy, which is if we are predicting skarn alteration, is how good the predictions were. So, for example, 90% prediction accuracy means 90% of samples were correctly classified. But this is in the training set. As I explained, you need to evaluate in the test set, because the test set is more unbiased because it hasn't seen the model fitting process. So what you do is to select a model that reduces this gap. So you see, for example, this support vector machine with radial kernels has a huge gap. What that means is that this model is kind of overfitting. It's kind of an equivalent here. It's kind of overfitting every data point. So it's giving you an apparent good results in your training data, but as new results come, it's not that great. So what we want is minimize this gap. And as I explained earlier, the random forest models are the best model, almost no gap between training and test sets. So it's very stable model. And we are getting close to 80% accuracy for this prediction of skarn mineralogy. As I explained before, this was in raw geochemical data. And then we fit it also in coordinates, isometric log ratio coordinates, because each data point was done 10 times. So indeed, there are 280 models in this, summarizing this graph. And we could do a statistical testing, inferential statistics, to see if we find any significant difference between the compositional representations and the raw geochemistry. In this study, we didn't find any difference, which means it's very empowering, because you cannot go wrong when you use a compositional representation, because indeed a lot of these methods are based for Euclidean spaces in the real space. So you can be confident that even these kind of transformations are going to still give you very good optimal results, and you don't have to worry about violating any mathematical properties of the space in which you are working. So I would encourage you to use compositional representations. Because we have in this test set with mineralogy and all of that, mineralogy, so we can actually assess the role of the core logging geologies, and the visual observations in the core, drill core, was 50% accurate. So this is an example where, you know, this kind of algorithmic modeling is gonna give you better performance. Even the algorithmic model, the worst algorithmic model, give you better performance than the core logging. So and that's one of the goals of machine learning, is to match or improve the models from what the human learning would be able to do. So it is important to, you know, understand how to evaluate these projects, especially since these methodologies are becoming more common in the mining industry. So if you are a manager making a decision how to evaluate the model, or you are actually an analyst, I would recommend one of the first things to look at is the confusion matrix. So here we have all the alterations that we are predicting. So by row we have the true classes, and by column we have the predicted classes. So the accuracy is basically if you take the summation of the diagonal of this matrix and divide it by the total of samples, then it's going to give you the accuracy, which is the 78%, means 78% of samples were classified correctly. And then there are other measures of model performance, which is precision and sensitivity. It can be a little bit confusing, so I'm going to explain here with an analogy. If you were to develop a predictive model to identify the thumbs of your hand, for instance, and then your predictive model identify 1 out of 1, then your precision is 100%, because you were, all the times you were correct. You identify 1 thumb and it was 1 thumb, so it's 100% correct. So the precision is 100%, but the sensitivity is only 50%, because you identify 1, but there are 2. So 50%. So in other words, precision is how good is your algorithm at identifying, like here, it's very good. And sensitivity means is how efficient is at identifying. So here is very good at identifying the thumbs, but it's not efficient because half of this class is not detected. So you want these two properties to be close. And you see in this particular project that there is a big gap between in the epi of the skarn, meaning you are very good at predicting, if you can call this number very good at predicting, but you are not very efficient at recognizing this class. And the reason for that is, when you look at here, is this class is poorly sampled. So there is a class imbalance here. So, and one of the reasons for that is that there is no economic value in the epidemic current. So people are not going to sample these in the same way that they sample all these other alterations that contain, and often, very often a problem in our industry, we focus only on what has value, but it really impacts the models. You have to sample everything basically to be able to create good models. Ultimately, this is the result that you want to get. I'm not going to explain this. This is a cross section of the deposit. It's done in leapfrog, showing all the stratigraphy alterations, etc. But that's the ultimate goal, to map. That's we're doing this because we still mapping is part of our main objective in our disciplines. Finally, I want to conclude this presentation with a take-home message, and let's recognize that geochemistry is compositional, so it lies in a mathematical space that is different from the Euclidean space. So we need to either do compositional representations or use the actual simplicial geometry to analyze our data, depending on the approach you do. But it's important to recognize that geochemistry is a special type of data, it's compositional. It's important to start any kind of modeling thinking on a fundamental question rather than just trying to throw principal component analysis and find meaning in those components. You really set the analysis with a fundamental question. Geological sampling techniques, none of these techniques is a replacement for poor sampling. So we still need to evaluate if the samples that we're using are appropriate to build a model, especially when those models are going to fit an economic evaluation of a mineral deposit or a metallurgical flow sheet model, for example. We also need to let geochemical analysis guide algorithmic modeling, and that implies assessing element mobility, understanding your digestion, and many more things that I didn't add here, but it's all about the geochemical literacy guiding your analysis. And then when you have done all of that, then you can really, with confidence, engineer our geochemical space so that you can get some really nice results. And if your results doesn't make sense, like in this case, in geological space, even if this cluster, like in this case, is mathematically correct, if it doesn't make sense in geological space, you have to redo the analysis, because at the end of the day, is the geological space the ultimate judge of your geochemical modeling. And with that, I want to leave this part. If you have any questions, just feel free to send me an email or discuss in our live session. Thank you.